Hello, my name is Marco Kaufmann. I'm CEO of the Simulics Corporation. In today's video, I'd like to present you our Reverse Debugger plugin for the MPLabX IDE. Reverse debugging offers vast new features for investigating software bugs. Developers can rewind their programs in the IDE, explore past program states, and even replay non-deterministic behavior. For demonstration, I created a small project here. It is a dry stone benchmark for the PIC24 Starter Kit. This is what the demo looks like on the real hardware board. Now we switch into reverse debugging mode. We enter the project properties and select the tool Simulics Reverse Debugger. In this mode, the program does run on a virtual target, rather than on the real hardware. The underlying platform simulator includes instruction set models for the PIC24 and the ARMv7 architecture. In addition, any device models like timers, UARTs or interrupt controllers can be embedded into the simulation. In our current example, the tool employs a platform model of the PIC24 Starter Kit, including its .matrix display. We can show this as an additional view by tools embedded in the menu. Now let's start simulation and see what happens. Take a look at the display. The unmodified program binary is executed on the simulator. It prints messages onto the display like it would happen on the real hardware board. Program execution can be suspended any time to explore or manipulate memory contents, set breakpoints and watch points, just like with a real hardware board. Now I enable this breakpoint inside the handler routine for the timer. The routine increments a variable named tick. After continuing program execution, we rest at this breakpoint again and we can see how the tick variable is incremented. As you may already have noticed, we have some additional run control buttons in the toolbar. With run reverse, we continue program execution in the reverse direction. The program runs back to the last breakpoint or back to its initial state if no breakpoint was hit. Take a look at the registers and at the tick variable in the watch window. As you can see, the variable is decremented because we move backwards in runtime. Now let us clear the breakpoint and continue program execution in forward direction until the program finishes. We rest now at the last instruction of the program at address 220. Let us step back some instructions with the Step Instruction Reverse button. Again, have a look at the program memory and at the SFR window. With Step into Reverse, we can step back one single line on the source level. Now I enable the breakpoint in the handler routine for the timer again. After a run reverse, we rest at the point in target runtime when the timer interrupt was released the last time before the program did finish. You can see the decrementing tick variable, and you also can see how the display clear is undone step by step. Another quite useful feature is the target timeline. it shows the current position in the runtime of the target. Instead of running forward and reverse using the run control buttons, we can also enter the requested position directly. For example, let us jump to the point in runtime where 50 millions of instructions had been executed. As you can see, the display was not yet active at this time. Now, let us see how things looked after 80 millions of instructions. Here, the display had already been turned on. By moving the slider, we can go back and forth on the timeline. Let us suppose we have a bug in a graphics routine that messes up some pixels on the display. Now we want to explore how pixels were built up on the display. We could do this by setting a breakpoint at the putPixel function at address 60cc and let the target run in reverse. Take a look at the display. Between the breaks, you can see how the single pixels are dismounted.